Hey students, this is a set of optics demos, some stuff you guys are missing out on in person. We're going to try to do remotely. So first up, I want to talk about this thing. This is a concave mirror. So it's curved. I don't know if you guys can tell. Yep, there you go. You can kind of see. Okay, it's curved in, and based on the law of reflection, any light that's going to come into this is going to get bounced kind of inward towards a focal point. So this is really far out. You guys can kind of see the TV computer there. And then this is zooming in, and we're approaching the focal point. And when we get there, it's going to change. And that's kind of crazy, right? Mr. Opal mentioned the weird blue color. Yep, he is totally right. All right. And then beyond that, so let's get that blue color back. Let's see. Oops, there we go. Beyond that, it'll now be bigger and right side up again. There's OBS Studio. You can kind of see some stuff going on. There's the edge of my computer. There's the keyboard. Okay, so now it's bigger and right side up. So that's kind of weird. So one thing we could do with this is we could make these things called a ray diagram, which we did not end up having time to practice this year. But basically, you're tracing light coming from an object, which represented by this arrow here, towards the mirror and a couple different possible pathways. And then when it gets to the concave mirror, you map out which way it's going to reflect using the law of reflection. That's where the incident ray makes the same angle with the normal compared to the surface of the mirror as the reflected ray on the other side of that. So basically bounce in, bounce out. The incident and reflected ray both make the same angle as compared to the normal, the line that's perpendicular to the surface. So you can map this out, and there's basically a set of rules you can learn pretty quick to follow, where it goes in parallel, bounces out through the focal point, goes in through the focal point, bounces out parallel, and then goes through the center of curvature and bounces straight back through the center of curvature. Now what's cool is you can apply some of those same rules to a different kind of mirror. The other curvature is called convex. What's weird about this is that it makes it seem like the light is coming from the other side of the mirror. So this is called a virtual ray back here, and it's going to produce a small virtual image. Let's try that other type of mirror out. So it should look to you like there's a much smaller object behind where the mirror is. So basically, yep, it's just far away, smaller, and behind the mirror. So that one is a little less crazy, but definitely is following what the ray diagram said it should. So that's good. We'll do that. Okay, now, what's a cool application for this mirror? Why do you care? Well, if you have a whole bunch of rays coming in from parallel, like some object really, oops, just kidding, haha. Some object really, really far away is shooting light through outer space. Let's say it's like the sun or something. And those rays are all going to hit the mirror essentially parallel. Where they're going to all bounce to is a focal point. And at that focal point, you can see all that light is overlapping. It's really concentrated. You're going to get a stronger signal, or you're going to get more energy located there. So like if you were to put a piece of paper here, and if this was sunlight, it might catch on fire. Or let's say this was radio waves coming from a satellite in outer space. What you could do is you could put this thing at the focal point aimed back towards the mirror. So it'd look kind of like this, 1/2 meter focal length, aim it up at the satellite. Yep. So let's say the satellite's up there. And then you put this thing, the receiver, at the focal point, and then you have this thing called dish TV, or whatever you want to call it. So basically those dishes on people's roofs, those are mirrors. They're not mirrors for visible light, they're mirrors for radio waves. So remember that the kind of light you can see is not the only one that's important. Anyway, yep, ripped that off a dish TV for when I first bought my house. Okay, next thing, what else could you do with this? You could have it come in and bounce to the focal point, but the other thing you could do is you could have it start from a focal point, bounce out, and come out parallel, and then not spread out anymore. So what I wanted to try to do one time was there was this kid in the back of the class, man. I don't know. What I wanted to do was set up a 150 watt infrared bulb, which nobody can see, right? Unless you're like a reptile. Like some lizards can see this. People cannot see this kind of light though. By the way, you're like, that's just a piece of black ceramic with some heater pads in it. That's not a light bulb. Remember, visible light is not the only kind. This thing is an infrared light bulb. It's like 250, 300 watts, something like that. It soaks up a lot of power. And so I was going to try to dish out a beam of infrared light, and then I was going to set it up kind of like this and aim it at that kid in the back of the room, you know, and see if I could get like a parallel heat ray. Just like, Mr. Worden, why is it so hot in here? Everybody else is like, what are you talking about? Anyway, be invisible. Anyway, it does not work. It's not enough power. This isn't a big enough size to catch the, you know, enough of the total power generated, but it was a fun try. Okay, next thing we're going to play around with. This is a ray box. Its whole intent and purpose is to make 5 parallel beams of light. Okay, so the light's going to start out parallel. Let me see if I have enough hands to demonstrate this for you guys. All right. So far, so good, right? So what I'm going to do is I'm going to show you, yep, see the spacing of that light beam? See the spacing of that light beam? Oops, I don't quite have it right. Let me try again. So you can, it's like a little bit adjustable. That stay pretty much parallel? Not quite still. Okay, let's try again. How about now? Oh yeah, okay. That looks pretty much parallel to me. So you can see even as it gets farther, the spacing between those 5 rays is staying the same. Cool beans. What I'm going to do next is I'm going to take a convex lens. It's thicker in the middle, it's thinner on the sides. Convex lens, actually double convex since it's shaped that way on both sides. I'm going to put it in front of the light beamer. Let's see if I can do this, sorry. So first up, parallel. And now, let's see, coordinate up. Okay, see how they're all overlapping at that spot? That is the focal point for this lens. When it's really close, they're not spread out yet. Now they're right at the focal point, all the rays are overlapping, and now they spread out. I can't cover the whole thing, so watch the, maybe I can actually. Yeah, there we go. I think I got most of them. So you guys can see that there is in fact a focal length for this lens. It's pretty short. It's the distance from the lens to where I was putting the beam on the board. It's only about 5 centimeters or so. So that has a 50 millimeter focal length. Cool. If I use the other curvature of lens, do you think it would be convergent or divergent? And the answer is if you got the opposite shape, it's going to do the opposite thing. So this lens made them converge, come together. A concave lens would make them diverge in that instance. All right, so that's the first round of demos, optics. We're going to switch to some other. All right, here comes the next round of demos. Okay, so for starters, we are going to take a look at this music box. It's got a closed end and an open end. What that means is we're looking at a node on this side and an antinode on this side when a wave function sets up inside here and makes a resonance. What we also have to do is we also want the box and the air column inside it to be vibrating at the same frequency as the tuning fork. If they work together, if they're sympathetic resonances, then we'll be able to maintain a high amplitude sound in here for a long time. If they're fighting each other, that's going to convert the sound into like thermal energy. It's going to basically dim it down and decrease the amplitude. And what we're going to hear is that the sound's going to fade really fast. So I think right now I've got it tuned for working well together. Let's give it a try. Not perfect, but hopefully you guys can hear that. And it is really loud right on that antinode. There is a lot of amplitude there. So right about just a little bit past the opening, right about here is the maximum volume you can get out of this thing. Okay, now what I could do with this is I could measure from the node to the antinode is about 30 centimeters. And I can actually go map this out. So here's some drawings. Here's a node to antinode, a little bit past the box, but basically right about here for our first harmonic, which is what's happening in there. That's 30 centimeters, which means the entire wavelength is going to be 120 centimeters, which means 90 centimeters past the box, things are going to start over, right? 30, 60, 90, 120. And then if I put the other box at 150, I should actually be able to get the other box to pick up that sound wave and also resonate in sync with the box. Now, one thing I want to do though is make sure these boxes are tuned together. So we're going to try to get the beats phenomenon going here. I'm going to see if they end up making the same pitch, the same frequency, which also go at the same wavelength. Yeah, those are really close. Okay, cool. So I'm going to measure out 150 centimeters. Oh, dang, we might not make it. Okay, new plan. Desk's not big enough. You guys won't be able to see it. Let's see. Where else could we put it? We could put the box right here. The other one. Because that way we've still got an antinode and a node. And that means we only need 60 centimeters between the two boxes. So we'll try that. Not quite as cool, but that'll do it too. So I'm going to put the box right here at 60. You guys can see both boxes. What I'm going to try to do is take the microphone and get it. I'm going to only hit this one. I'm going to mute this and then put the microphone right here. And we'll see if we've magically transported sound across time and space. Let's see, they're aimed up. Here we go. Alrighty. Ta-da! I don't know if you guys can hear anything because I do have a noise gate on the audio filters too. I didn't think of that. Shoot. Hopefully you guys could hear that okay. Anyway, audible to me. It's working. We just built a frequency cannon. We teleported energy from this one to this one. Nothing was connecting here but air. By the way, could you have not air connect that or no? It's a mechanical wave. You got to have the air. Okay, next thing. Next thing we're going to do is we're going to do another tuning fork demo. This one is to find the speed of sound, which you guys should know after having passed that quiz, hopefully, is 343 meters per second. Okay, so what I'm going to do is I'm going to have a pipe filled with air. Don't worry about the water. That's not important. The sound's not in the water. It's in the air. We're going to measure the length of the air column when I get a resonance. Now my tuning fork has 256 hertz frequency. So I already know the frequency. What I'm going to do is measure something about this. When I hear that the tuning fork and the pipe match up, I'm going to hear a humming. That's a resonance in the pipe of the sound from the tuning fork at the same frequency. And then once I know that, I'll be able to figure out what the wavelength of the sound is and then use the wave equation to find the speed of sound. You guys hear that high-pitched? That is actually an overtone. We don't want that. It's right at this spot right here. That is a 17 centimeter overtone. I already measured this out. That's not the one we want. Let's keep going. All right, so I guess I'm just barely off camera, sorry. Right about there is the fundamental, the first harmonic. We measure that out. It says 34 centimeters, okay? So next up, I get out my pre-made whiteboard. We had a 17 centimeter overtone we're ignoring. 34 centimeter fundamental, that's the first harmonic. It was on this node to antinode pattern inside the pipe, closed end to open end, closed end by the water, open end just to the air. Tuning fork is just past that. Tuning fork said frequency is 256. Since this is a quarter wavelength, it needs to go all the way back out. then my full wavelength isn't 34 centimeters, it's 1 meter and 36 centimeters, 1.36 meters. I just took this number times 4, converted it to meters. Plugged it into my wave equation, v equals lambda times f, velocity is wavelength times frequency, and I got a speed of sound of 348 meters per second, which is pretty close to the accepted value of 343 meters per second. So not bad. That's kind of cool. Alrighty, next thing we're going to do is a crazy one you're probably glad you're not here for, which is the resonant rod. So what I'm going to do is I'm going to put more waves in the rod at exactly the right frequency and timing. So it's all going to be the same frequency, but I'm going to put them in a way that constructively interferes, not destructively interferes. So each time I add waves, it's going to get louder and louder inside the pipe and also outside the pipe. Hopefully nobody thinks there's an alarm going off or anything like that. It is so loud. It's still going too. This one really hurts. So here's my question for you guys. First of all, why am I holding it exactly in the middle? And what happens if I hold it over here? Oh, that didn't work. I can only hold it in this spot. I can't hold it anywhere else. Why? Well, because I'm setting up a standing wave inside there, which is when you have an incident wave and a reflected wave interfere in a way to make a pattern with nodes and antinodes. And I was holding it at a node, which means since nothing's going on there anyway, I'm not diminishing the amplitude by holding it there. And I kept putting more and more in so that this constructive interference built the wave up to a higher amplitude, which you will also notice as a louder volume in a sound wave. So hopefully that kind of makes sense there. It's a pretty cool one. The trick to this is to use some violin rosin. You just basically rub the rosin on the rod and also get a little bit on your fingers, and then you can actually get it to grip just right. And at that point you can drive like a harmonic resonance, which is pretty sweet. Alrighty, I'm gonna set up for some more. Alrighty, so we're back with some more stuff. First up, we're just going to get the Slinky going. Slinky is a great teaching tool for waves. I'm going to make 2 different kinds of waves here. I want you guys to tell me which kind it is. Okay, that's one kind. That's another kind. Hopefully you're thinking this first one is transverse. And the second one is longitudinal. Look at the direction I'm moving my hand compared to the direction the wave goes. In both cases, the waves go, back and forth this way, right? Like that wave travels right and left. But I'm moving my hand forward and backward, right? As opposed to moving my hand the same direction the wave goes. So that's longitudinal, also called compressional. This is transverse. Both of these waves involve the Slinky as a medium, which makes them mechanical. They are both physically manipulating the medium here. Okay, so got these 2 wine glasses. One's got a little more water than the other. I'm gonna make these things resonate. They're going to be in what's called simple harmonic motion, which is basically like waves confined to a space. It's basically just like a back and forth motion, which is like a wave. It has a lot of the same properties. What's important is that it's the glass that's moving. And the water has a lot of inertia, a lot of mass. So which of these, the full glass or the half full glass, is going to be easier to push back and forth? I want you to think back to Newton's second law. Force equals mass times acceleration. If both of these are identical glass doing the pushing, the one with the higher mass is going to accelerate slower. The one with the lower mass, because there's less water in it, is going to accelerate faster. This one is going to be able to wiggle back and forth quicker. It's going to be able to do more oscillations, more back and forth motions. It's going to have a higher frequency. This is going to have a lower frequency. A lot of people think it's about the air column in the glass. It's not. It's the glass that's moving in this case. So with that, oop, I was getting some undertones there. That's weird. There we go. I don't think you guys can see it on the camera, but there's actually a whole bunch of rippling action right on the water itself where it interfaces with the glass. So like right at the edge of the glass and water, that boundary, there's some crazy wave patterns happening on the water. It's pretty cool to see. You guys can try this at home if you have some nice wine glasses. Okay. Right? That one got to be a lower pitch. Getting some overtones and squeaks in there and some ghosting, but in general, lower pitch. Because the water is hard to push back and forth. It's got a lot of inertia and it slows down the oscillation, lowers the frequency. Now, which ripples in the water are closer together? Which one has finer, smaller, more detailed ripples in the water? Hopefully you picked a high frequency goes with a small wavelength, and a low frequency goes with a longer wavelength. So this one, the ripples look bigger. This one, the ripples look smaller in terms of their spacing close together. By the way, just a quick picture of the way the wine glass oscillates. You're wobbling some sides out and other sides in. It might not be a multiple of 2. It could be a multiple of 3 or 4 or something like that. There's going to be some kind of harmonic series to it, and I'm not sure which resonance I'm hitting. But basically, it is the glass that's moving and flexing in a circle. So hopefully that's pretty cool. All right, let's do something even cooler. So far, we've done a whole lot of mechanical waves. I would like to see some electromagnetic waves. So I was thinking, first of all, a microwave, what kind of waves does that make? Makes microwaves. That's one of the categories on the electromagnetic spectrum. About how big is the wavelength for a microwave? It's about somewhere in the like 1 to 20, 1 to 30 centimeter range. It's about 10 centimeters across. Okay, so this is a wavelength, which got me to thinking, got this box, they're always about the same size. One reason for that is you need to be able to fit a small turkey, the biggest thing anybody's gonna cook. Okay, second reason is maybe from where the microwaves are emitted at the magnetotron, it's setting up a nice standing wave. It's going to have some resonances, and that'd be cool, right? Now, other thing is, what is an electromagnetic wave? It's an electric field and magnetic field both changing. Well, hey, if you have an electric field change, while there's an electric field up, you can push electrons from one side to the other side. And then when you change it, they'll go back the other way. You can basically get electrons to go back and forth, which is what we call electricity. So I got this light bulb. It's got these metal chunks on the end. Metals where you can, easily get electrons to flow around. If you've had chemistry, you know something about why. It's that sea of electrons bonding model. And if we apply an electromagnetic field to it, we should be able to power this thing. All right, putting light bulbs in the microwave. Do not do this at home. Only at my home does this get done. Woo! Okay, let's do it again. Woo! All righty. So, oops, caught my mic there. All right. So, this light bulb is warm. Here's a big problem. That is a 1,000 watt microwave. This is a probably 4 to 8 watt bulb. So power input, power output, do they match? Is this piece of gear rated for that power? No. That's why you don't leave it going. That's why I turned it off after like 1 to 2 seconds. It's already warm. So we're basically way overloading the bulb. But good news, we converted electromagnetic waves into electromagnetic waves. And you're like, well, wait a second, did we really? No, we did. We converted them from microwaves, which you can't see, into visible light, which you can see, both of which are electromagnetic waves. We just used this piece of technology to be able to convert. So, and we lost a bunch to heat in the process because entropy wins, you lose. Okay, let me get a better idea. So I was thinking, well, cool, it's nice to light light bulbs up and all, but I want to know is that microwave, does it have a resonance or not? So I went on eBay and I found a Russian vendor who was selling Chinese light bulbs like this, but for cheap, because otherwise this thing would cost me a ton to build. So I built this thing. I built a grid of Chinese, Russian-made, whatever light bulbs on an acrylic plate that fits perfectly in a microwave. Now, I want you guys think back on how I held the rod. I held it right in the middle, right? Because that was a node, and there was no energy being delivered or lost at this point. All the energy was up here or here, right? That's where it's got amplitude, at the antinodes. So here's a hypothesis. If I put this in the microwave, and the microwave is in fact resonant with a standing wave, and its wavelength is kind of somewhere in these dimensions, I should see the ones at antinodes light up like crazy, and the ones at nodes not light up at all. That's the hypothesis. Let's test that thing. Oh yeah. Bazillion microwave light bulbs going in. It's like it was made for that. Okay. Let there be light. Woo-hoo. Okay. Let's do it one more time. All right. I don't know if you guys can tell from way over there. The vast majority of those are lighting up at the same time. Now I eventually figured out what I did wrong. In a string, you're only worried about one dimension, right? In a plane, you're worried about 2 dimensions. I built this to map out the resonances across a plane. See how that grid's got X and Y coordinates? But does it have light bulbs stacked this way? Does it also have Z coordinates? No. So what I'm trying to do is I'm trying to map a 3D resonance into a 2D space. That's not completely working. So like you might have a node here, but you might have an antinode here, and you might have a node again here, and you might have an antinode there. So overall, the bulb still gets power. That's kind of a bummer. This didn't work. And I couldn't find light bulbs that were like small enough of the right variety to build a vertical stack. Plus that would have also taken forever and been super expensive. So yeah, there is that. Anyway, we still get to put light bulbs in the microwave today. All right, let me re-gear for the next couple demos. Alrighty, next demo we're doing is we are looking at some different... Oh, I unplugged that, just kidding. Next demo we're doing is the trumpet. Okay, so first up, we've got a constriction right here. We're gonna get a node going. We've got an antinode projected just past the bell, which is kind of the point of the bell. The harmonic that sets up basically does the full loop-de-loo of the trumpet. So from here to here is the distance that we're multiplying to get the wavelength. What I can do is I can start this on the first harmonic, also called the fundamental, and I'm controlling that with my lips. Then I can go up a notch to the second harmonic, to the third harmonic, to the fourth harmonic, etc. So I can control, using lip musculature, which harmonic you're driving in the trumpet. That's part of like learning how to play it. And then the other thing I can do is I can change the distance from here to here. I can make it longer by using the valves. The middle valve is worth 1. The next valve is worth 2. This valve is worth 3. And so in different combinations, by holding down valves, you can make it like you can basically extend the instrument's wavelength out, and bigger wavelengths will go at lower frequencies. So by pushing valves down, I'm actually lowering frequencies. Okay, so here we go. Bum, 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 bum. Bum, 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 bum. I forget the rest of that. Anyway, it's been a while. Okay, so what I'm going to do is I'm going to start on the third harmonic. I'm going to use the valves to go down in a chromatic scale. Then I'm going to suddenly let go of the valves and switch to the second harmonic. Then I'm going to repeat that process using the valves to go down, and finally I'll end up on the first harmonic, and in the process I'll have played a scale. Okay, so remember, 1, 2, 3, different combos. You'll see me walk down different combos. I'm going to start with 0, 1, 2, 3, or 3. I'm going to use this one, but you could do that too. And then 4, 5, 6 if I need it. So you can get up to a total of 6. 1 plus 2 plus 3. Okay, here we go. So what you heard was 3 different harmonics. And in between, I extended the wavelength and therefore lowered the frequency using the valves. So I'll do that one more time. And then if you can really control it, sometimes you can go some tones lower than that, which is pretty fun. Okay, so there's that. How a set of harmonic series and resonances and changing lengths works for a air-powered instrument, either brass or woodwind instrument, not necessarily the same as a string instrument. They also rely on tension and the mass of the string, but same stuff. What I'm going to do next is I'm going to put in a silencer, and it's got a mic in it. When it's silencing, what is it changing? It's changing the amplitude. So it's dropping the amplitude down to the point where you guys can't hear it anymore, or at least not very much. Okay, now, interestingly enough, the pickup mute I've got running through an amplifier, which I've then got going to this thing called an oscilloscope, and its job is to capture really fast wave functions on the screen for you to look at, and it's actually basically built off graph paper. You can control the scaling of the graph paper over with these knobs here, and you could even go in and measure what the amplitude and what the wavelength is. Oh, actually, this is going to be a function of time, so this would be what the period is, not the wavelength. This is a graph of time versus amplitude. Okay, so I'm going to play some low notes. A wavelength, that much, whatever that's worth. If I go higher, are you going to see the wavelength get wider or shorter? Higher frequency would cause lower wavelength. The two always multiply out to the same speed of sound. I'm actually clipping. Well, I'm not sure why I'm clipping, but hopefully you saw the wavelengths get closer together. Sorry, the periods get closer together. Shorter period, higher frequency, higher note. Other thing we're going to do is I'm going to play a quiet one, and then I'm going to blast a really loud one. What do you think the difference is going to be that time? Hopefully you're thinking a bigger amplitude. So the graph got taller, bigger amplitude. Now a couple other things happened. That didn't sound the same, right? Like it sounded different. It's both trumpet, but like one was mellow, smooth trumpet. The other was like harsh, buzzy trumpet. And what you're noticing, hopefully, is that this is not a simple sine wave. This is a really complicated shape. And that complicated shape is multiple waves being added together. They're overlapping and they're interfering to create a compound wave. And that shape is what our ear processes as the sound of trumpet in different styles. So if you can recreate that shape, you can actually, make a synthesizer or whatever. That louder shape is a lot more jagged, and it's also going to go with kind of a harsher tone. Here, I'll play that without the mute so you guys can hear it. So very different sounding. Cool. So that's an oscilloscope. You can analyze all kinds of cool stuff with it. Let's go on to the next couple things here. I'm going to re-plug in some stuff. Turn this off. We're going to switch plugs real quick. Won't take long. All right. So next thing we're going to do is that tube is filled with neon. So what you're looking at is a neon light. It's made of neon, the element neon. Now we talked about spectroscopy, which is spreading out all the colors of light and then analyzing them. What I have here is a diffraction grating. It's some special plastic with lines cut in it. And the lines act as barriers, and that way the light can go and bend around the barrier. So what I'm gonna do is put that over the camera. You guys are not gonna be looking directly at the light. You're gonna be looking to the side where the light has refracted from. And we're gonna be looking for the spectrum, which is like the fingerprint of neon. So let's try that out. Let's see. It's like, see, it's projected kind of right on the edge of the table. Kind of see underneath the fire blanket. See those two yellow and then a couple red lines? That is the emission spectrum of neon. Now, if you saw that same pattern from like a star somewhere super far away, you'd know that there was neon in the star. So hopefully you guys can see kind of right where that cord is underneath the fire blanket, that set of lines, that's the spectrum for neon. So then let's try some other stuff out. Neon's the best one because it's the brightest, it works great. We'll see if I can get some other ones to work for you guys too. Next up, it looks like we're trying water vapor. Oh, yeah, that's not happening. Okay, next up we are trying mystery element C. Used to be a lab where you try to figure these out. Oh, that's one of the noble gases. I can't remember which one. Okay, so let's see if I got this set up right again. Anything. Bueller. Let's see. Oh, maybe I need to rotate it. Oh, yeah. I can see like, okay, a little farther in from the edge of the table because it's not refracted as much. I can see a yellow line and then a couple real faint green lines and then a purple line. The purple lines are almost where the white lid on the wall is. So let's see if I can, oh man, I don't know if I'm this coordinated. Oh, purple line. And then yellow line. And then I can see it, I don't know if you guys can, but there's a couple lines right in there. Oh, of course my finger covered it up while it was happening, so that didn't work, right? But there we go. So that is mystery element C, whatever that is. And we could go compare this with some known elements and we could actually find out which one that is. So this is called spectroscopy. It's how we know what stuff is made out of. You can check one element at a time and figure that out. It's pretty cool. All right, what we're back for right now is, for starters, I've got a solar panel here. I got it pretty dark in the classroom, so we are not getting too many volts, and hopefully you can see that right there. Cool, so not too many volts. Now here's my question for you guys. I'm gonna put 3 different light bulbs on them, and I want you guys to guess which one is gonna make the highest voltage. The first light bulb I'm gonna try is 233 watts of input power. It is a very powerful light bulb, and it is an infrared light bulb. The second light bulb is also quite powerful. It's a 150 watt incandescent bulb. Incandescent bulbs, they're bright because they're hot. And then the last one I'm gonna do is a 16 watt, I can't remember if this is, I think it's a LED. Yeah, a 16 watt LED bulb. And what I graphed right here is the spectrum. I exaggerated a bit, but kind of sort of spectrum that they're making. So which one do you guys think is going to produce the highest voltage? The 233 watt bulb, the 150 watt bulb, or the 16 watt bulb? Let's try them out. All right, first up, looks like I've got plugged in the wimpy 16 watt bulb. Woo! Here we go. And I'm going to put that smack dab on there. And cool, we're getting just under 10, yeah, right around 10 volts. Okay, that is with the wimpy 16 watt bulb. Now we're gonna switch out and do the incandescent bulb. There we go. Watcha! That's a bright one. Okay, here we go. Also, this one's just a nice steady little over 10 volts, about the same as the 16 watt bulb. Now that's weird, right? Like, how can a 150 watt bulb and a 16 watt bulb cause the same voltage and corresponding power output on a solar panel? They don't have the same input power, that's for sure. Okay, let's try another one. Now we're gonna go up to the super duper 200, whatever I said it was, bulb. I measured them all with a kilowatt meter system before we started this video here. Ready? 250 watts. Wacha. And you're like, nothing's on. Nope, it is pulling 234 watts right now. It is in fact on. And if I put my hand here, it is getting quite warm. Anyway, let's hold the solar panel up to it. Well, that's not working. But this bulb is consuming 234 watts. Huh. All right, so let's talk about this. Hopefully you guys are thinking this has to do with the photoelectric effect. This is the effect where light acts like a particle. Individual pieces of light we call photons. Each one has a certain amount of energy, and the amount of energy they have corresponds to their frequency. So energy corresponds to their frequency. H is just a constant, Planck's constant. So the higher the frequency, the higher the energy. Now here's the problem. The infrared bulbs was super, super powerful, like a lot of photons coming out, but each photon had such a low frequency that individually it didn't have very much energy, and it wasn't enough to lift the electron clear of one part of the solar panel and move it to the other. And that's what you need for it to start to stack up electrons, build a voltage, and be able to push a current. So this thing's made out of silicon in zones, 2 different zones connected together called a diode. And they have some different elements added in with either extra electrons or missing electrons called holes. Electrons fall in the holes, and when you get light on here, you can have the energy from the light move the electron back out of the hole to the other side, at which point it starts to generate voltages for you, because stacking up electrons makes an electric field. So that's how a solar panel works. This is kind of an example of the photoelectric effect. A whole lot of infrared light. Each individual photon was not enough to lift an electron, so nothing happened. On the incandescent bulb, most of what it was emitting was infrared, but it did include some visible light, which is why it at least got 10 volts out on the panel. And that was radiation production because it was hot, so that was black body radiation. And then the last one, the other one we tried, the LED, all of the energy that it was using, minus what entropy took as a cut, was converted to visible light. So all of the light coming out of that was visible light, which means that all of the light worked. It was successfully able to lift the photon high enough to move it to another zone each time it tried. So basically, this is like the first bulb, let's say it was trying to lift a brick. I should go get the brick. We always need the brick. Okay. So I want you guys to imagine there is a shelf here. And let's say you try to lift the brick 10,000 times and let go of it, and each time you lift it this far. Does the brick ever end up on the shelf? No. That was the example of the infrared bulb. We tried a lot, but each time we only lifted it a smidge and it fell right back down. It never got to where it needed to get the solar panel to be able to work. Okay, the incandescent bulb, it tried a whole lot as well, maybe half as much. Let's say it gave it 5,000 trials to lift the brick. Some of them it barely moved it at all. Some of it moved it a lot. Some of it moved it a lot on a very rare occasion. And then sometimes, most of the time it was in here somewhere, which was a little bit shy of where it needed to be. And each time it tried to drop the brick from different heights. Some of those heights worked. Not very many, but some of them did. And that's why you saw it read about 10 volts. And then the last one, it might have only tried, let's say the wimpy 16 watt bulb, let's only give it 100 tries, but every single time it tried, it lifted it the exact same height to above where we set the shelf. So every single try worked. Even though there were only 100 tries, it was still one of the most successful light bulbs in getting the solar panel to generate voltage. So that's kind of a weird way of explaining the photoelectric effect. That's how we demonstrate that light is a particle. Now, what else is light? It is a wave. So what I've got is a laser, and I can't see in the dark. There we go. And I've also got some diffraction gratings. One of these is just basically screen mesh. And what I can do with this is I can beam a laser through here. We'll put it on the back wall. I think you guys will be able to see that. Can you see it? Maybe you cannot. Hold on, let me set up some more bricks to hold a thing to show you guys another thing. Just a sec. Ta-da! Cool holder screen. Not too far from the camera. I'm gonna go way over there. I'm gonna shine the laser onto the target. You guys will see it. It's a red laser. There you go. Now what I'm gonna do is I'm gonna put up that mesh in front of it. And hopefully you can see that two things happen. First is that in the directions of the mesh, it's bending around the barriers. That's diffraction. The second thing that's happening is as multiple waves interfere with each other, in some places they're constructive, in some places they're destructive. That's going to make a whole bunch of alternating light and dark spots. So the laser is diffracting and interfering. This is the double slit experiment on a larger scale. This is with a whole lot of slits because it's just basically mesh. And it's demonstrating that light is a wave. So light is both a particle and a wave. I also have a mesh that's even finer, and I think I have a second working laser of a different frequency, so we'll try out some different combos here. Here's, once again, the very coarse mesh. It's diffracting a little bit. I'm like clear on the other side of the room. It's diffracting a little bit, not a ton. If I switch to the finer mesh, we should get better diffraction. Oh, yowzer, look at that. That's like super good diffraction. You can also very clearly see the interference pattern. There are places where the light just isn't showing up with any amplitude. Those are the dark spots. That's where we have destructive interference. And then there's also bright spots with constructive interference. Now I'm going to switch to a different frequency. There we go. Here's green light. It is a shorter wavelength. That means the diffraction's not working quite as well. It's not bending as wide. The red laser went off screen easily. This one just barely goes off screen. It's not like widening out around the barrier as much. It's a worse match. But we're still getting the exact same, diffraction plus interference equals the fact that it's a wave. Here's with the really coarse mesh. It'll probably barely diffract at all. There's a mismatch between the wavelength and the barrier size, so it causes less diffraction. All right, cool. Hope you guys like that.